All right, welcome to the Explainer. Today, we are completely tearing down and demystifying the foundational concepts of electrical circuits from the ground up. Whether you're revisiting these core ideas or you're seeing them for the very first time, we're going to make the underlying physics clear, highly structured, and most importantly, tangible. You know, invisible electrons and complex math can get pretty abstract, right? So to really wrap our heads around how we harness and control this invisible energy, we're going to lean on a classic but super powerful analogy, a plumbing system. It sounds incredibly simple, I know, but visualizing electrical engineering through the lens of water pipes, pumps, and valves is literally one of the best ways to truly grasp what's going on under the hood. So here is our roadmap for today. First, we'll decode some core electrical terminology, then categorize our circuit elements, meet the RLC trio, and finally, take a close look at electrical power sources. Kicking things off with Section 1, decoding the basics of electrical terminology. Okay, so there's a really interesting distinction here that often trips people up. The difference between an electric circuit and an electric network. It's actually pretty simple. A circuit absolutely mandates a completely closed, unbroken path for electrons to flow from a source. A network, on the other hand, it doesn't necessarily need that closed path. So a great rule of thumb to keep in your back pocket is that all circuits are networks, but definitely not the other way around. Because a network without a closed loop is just, well, not a circuit. Let's move on to our very first primary metric, which is current. Sticking with our plumbing analogy, think of current exactly like the physical water rushing through a pipe. In our world, it's the movement of free electrons. Oh, and quick side note, it's always worth remembering that while actual electron current flows from the negative terminal to the positive terminal of a source, conventional current, the one we usually map out on paper, is drawn flowing from positive to negative. Just a quirky historical holdover. Now, mathematically speaking, we calculate this flow using a pretty straightforward formula. Current, or I, equals the derivative of charge, Q, with respect to time t. Basically, Q is our charge measured in coulombs, and t is our time in seconds. So when you divide those out, you're literally just getting the time rate of flow. And that gives us our primary measurement, amperes, or just amps for short. Next up is voltage. If current is the water flowing through the plumbing, then voltage is the pressure. It's the actual force that physically shoves that water through the pipes. Formally, it's defined as the electromotive force that causes the charge, those tiny electrons, to actually get up and move. Bottom line, without voltage, there is zero current. Nothing moves without that push. And if we look at the math for that pressure, it's V equals dW over dQ. In this setup, W stands for potential energy, measured in joules, and Q is, again, our unit of charge. So voltage is basically just the potential energy per unit of charge. And the result? Volts. Pretty intuitive when you break it down like that, right? Moving right along to Section 2, categorizing elements. Let's look at the types of components we are working with. So now that we've got our flow and our pressure totally locked down, it's time to classify the physical components we can actually plug into this plumbing system to make it do useful work. We can drop these elements into a few very distinct buckets. First up, active versus passive. Active elements, like power sources, literally deliver power to the circuit. Passive elements just absorb it, either burning it off as heat or storing it for later. Then we have bilateral versus unilateral. A bilateral element is easygoing. It lets current flow identically in both directions, offering the exact same impedance either way. A unilateral element, totally one-sided. It only likes current flowing in one specific direction. Finally, lumped versus distributed. Lumped components are the tiny self-contained ones acting all at once, whereas distributed elements, well, think of a massive miles-long power transmission line. Those parameters are spread all the way down the entire line. Another incredibly crucial part of categorizing these things is checking an element's, let's call it its personality profile. Engineers refer to this as its VI characteristics. Basically, we're trying to figure out if the relationship between the voltage across an element and the current running through it obeys the property of linearity. Does it form a nice, perfectly straight line on a graph? When you compare a linear and a nonlinear profile, the difference is just night and day. A linear element maintains this beautiful straight line, passing perfectly through the origin. That tells us it has a constant impedance, completely regardless of the current or voltage level. But then look at a nonlinear element. It has this bent, disjointed trajectory. Once the current hits a certain threshold, say 5 amps or maybe -3 amps, bam, the relationship completely changes. That right there is a classic nonlinear unilateral characteristic. It plays by its own rules. All right, that brings us to Section 3, meet the RLC trio. The resistor, the inductor, and the capacitor. These three components are absolutely the most fundamental passive elements you're ever going to use in network design. Let's start with the R, which stands for resistor. Now, a resistor does exactly what it sounds like it does. It acts like a physical narrowing or a pinch in our metaphorical water pipe. It deliberately restricts how fast the water can rush through. We intentionally use them to limit current flow or to chop up and divide the voltage across a circuit. If we apply Ohm's law here, which is probably the single most famous equation in all of electronics, V equals IR, we see that current is directly proportional to the applied voltage and inversely proportional to the resistance. Simply put, the higher the resistance, the lower the current for any given voltage. It's a fundamental trade-off. Next up in our trio is the inductor, which we represent with the letter L. Imagine an inductor as a coiled-up section of our water pipe. Because it's literally constructed from coils of wire, it actually produces magnetic flux whenever current flows through it. And the really cool part is that the total magnetic flux it produces has a direct, linear relationship with that flowing current. Now, the behavior of that inductor is totally dictated by Faraday's law. The voltage across the coil is entirely dependent on the rate of change of the current over time. So what does that actually mean? It means the inductor essentially fights against any sudden, rapid changes in current. It's doing everything in its power to keep the flow of our water perfectly steady. So the most crucial takeaway here is how each member of this RLC trio manages energy. Because spoiler alert, they handle it very differently. Resistors simply absorb power and burn it off, permanently dissipating it into the environment as heat. Inductors, like we just talked about, momentarily stash that energy away in the form of a magnetic field. And rounding out the group, capacitors hold onto their energy by storing it as an electric field, trapped right between two conducting plates separated by a dielectric medium. When you put them together, these three passive elements literally form the core of almost every single electronic device you own. Pretty amazing. And finally, let's jump into section 4, power sources, the active components driving the whole system. Okay, so we've got our pipes, we've got our narrowings, we've got our coils. But to actually make this entire system run, we absolutely need to introduce power sources. These are the active elements. They are the heavy-duty pumps driving our entire hydraulic network. Now, when we categorize these pumps, an independent source just does its own thing. It pumps out a fixed voltage or current entirely unaffected by whatever the rest of the network is doing. A dependent source, though, it's highly reactive. Its output depends strictly on a voltage or current happening somewhere else in the circuit. And then we have ideal versus practical. An ideal source is this flawless mathematical concept with zero internal resistance, but a practical source, that represents the messy real world, where internal resistance ultimately causes a drop in our output pressure. To really visualize that ideal perfection, if we actually possessed an ideal independent voltage source, its VI characteristic graph would just be a beautifully flat horizontal line. It would maintain exactly the same constant pressure, the same voltage, no matter how much current is furiously flowing out of it. But, of course, back in reality, physical batteries and generators have internal resistance, so as current goes up, that perfect horizontal line eventually starts to droop. Ooh, and just a really quick vital pro tip for the next time you're reading a circuit schematic. If you ever spot a diamond shape instead of the standard circle, you are looking at a dependent controlled source. These come in 4 different flavors, depending on whether they control voltage or current, and they are absolutely essential when we need to create equivalent models for complex, real-world components like transistors. All right, we've covered a lot of ground today. You now understand the basic terminology, the pumps, the pipes, and the pressures. You definitely know the difference between an active source and a passive resistor, inductor, or capacitor. You essentially have all the foundational pieces of a puzzle right in front of you. The invisible is finally structured. So the question I want to leave you with today is this. Armed with these fundamental building blocks, what intricate, world-changing engineering marvels are you going to design next? Keep exploring, keep building, and I'll catch you in the next explainer.